To look at nucleophilic substitution, and our main focus will be SN1, which is nucleophilic substitution first order, and SN2, which is nucleophilic substitution second order. So the first thing, we are going to define what nucleophilic substitution is. Then we are going to now compare SN1 and SN2. Then we will understand the mechanism for nucleophilic substitution first order and nucleophilic substitution second order. Then we'll also look at the factors affecting each reaction, and then we'll deal with the mastering and answering exam questions. So let's get into it. So with me here, this is an exam question asking about SN1 reaction. The topic is SN1 reaction mechanism. The question is 2-bromo-2-methylpropane react with water to form 2-methyl-tropropano. State the type of reaction occurring, draw the complete SN1 reaction, identify the rate determining step, explain why a tertiary alkyl halide undergoes an SN1 reaction more readily than a primary alkyl halide. Then there's another question here, which is SN2 reaction mechanism, and the question is 1-bromopropane react with aqueous sodium hydroxide to produce propan 1-O. Then states the type of reaction occurring. B, draw the complete SN2 reaction mechanism showing the backside attack of the hydroxide ion. Then C, explain why the reaction occurs in a single step. D, states the stereochemical outcome of an SN2 reaction. It is quite tricky to answer these questions without understanding the concept of SN1 and SN2. So it is very essential for us first to understand the concept, to know the difference between SN1 and SN2, then to get back to these questions so that we can answer them and also ace these exam questions. Okay, so let's now start by looking at SN1 and SN2. Then we shall come back to these questions. Alright, so we'll start by defining what nucleophilic substitution is. Okay. Alright, so let's first start by defining what nucleophilic substitution is all about. So, nucleophilic substitution. So, nucleophilic substitution is just a reaction where a nucleophile is able to attack a carbon atom and substitute or replaces a living group. So we are saying it is just a reaction. This is just a reaction where a nucleophile attacks a carbon atom and substitutes or replaces a living group. So that is all about nucleophilic substitution. It is just a reaction where a nucleophile attacks a carbon atom and substitutes or replaces a living group. So when you are talking about a nucleophile, We define a nucleophile as an electron-rich substance. So a nucleophile is a compound which is electron rich. So a nucleophile, we are saying it's a compound which is electron rich, meaning that it has a lot of electrons. But when you're talking about an electrophile is simply a compound which do not have a lot of electrons, so it is electron deficient. So an electrophile is a compound is a compound which is electron deficient. So that is what we need to understand there. Now let's look at a general equation for nucleophilic substitution. So a general equation would be, so we have this compound, and now this is just an alkyl chain bonded to a certain substance, which is X, which can be a halogen or any living group, then plus a certain nucleophile. So what happens here is that this group is able to live. So this group will live. Okay, then this R group, when that group leaves, a good living group, when it leaves the alkyl group to have a carbocation with a positive charge, then this nucleophile will attack this carbocation. Then when this happens, we're going to have an alkyl group bonded to this nucleophile, then plus the living group which left, which is that. Okay, so one thing we need to understand here is that this R group can be an alkyl group. This can be an alkyl group. Then the X can be a living group. And this living group can be something like a halogen, for example, a chloride, a bromide, or maybe an iodine or an iodide, should I say. Then, of course, we know that N is simply a nucleophile. Then the product is simply the alkyl group bonded to this nucleophile. So this is what we need to understand. Once you understand this general equation, trust me, it will be very easy for you to be able to solve these exam questions which they ask about nucleophilic substitution, either it is SN1 or SN2, because you have this prerequisite information and also an image of what a general equation should be. So now at this point, let's now try to understand the differences between an SN1 reaction and also an SN2 reaction. So for an SN1 reaction, we said it is just simply a first order nucleophilic substitution. So this we call it as first order. This is simply a first order substitution. substitution, nucleophilic substitution reaction. So I'm going to write it here. So this is what they simply mean when they say SN1. It is just first order nucleophilic substitution. Then when we talk of SN2, SN2 simply mean that you're simply referring to second order nucleophilic substitution. So that is what you need to understand. SN1 first order nucleophilic substitution, SN2 it is second order nucleophilic substitution. Now let's look at the differences. So differences between SN1 and SN2. Okay, let's understand the differences between SN1 or first order nucleophilic substitution and SN2, which is second order nucleophilic substitution. The first difference we must understand here, if I say SN1 this side, SN2 this side, one thing we need to understand about these two nucleophilic substitution, just like the name SN1 suggests, we simply mean that there is a nucleophilic substitution or a substitution of nucleophilic which is unimolecular. So one thing about SN1 is that this is unimolecular. Then SN2, because SN2 we are saying it is a second order nucleophilic substitution, so this is bimolecular. Then the other difference which we must understand, it's about the mechanism. What is the mechanism for SN1? So the mechanism for SN1, it is two-step reaction. This is two-step. It is two-step reaction. But for SN2 reaction, it is just one-step reaction. So SN1 it is two-step reaction, but SN2 is simply one-step reaction. Then the other difference which we must understand about these two reactions, it is about the intermediate which is formed. When you're talking about SN1 and SN2 this side, so for SN1 reaction, there is what is known as the formation of a carbocation intermediate. Here, SN1, there is a carbocation intermediate. Okay. So for SN1 there is carbocation intermediate, while SN2 there is no formation of carbocation intermediate. So we are just going to say no intermediate. So we should be able to understand that. Then when we look at another difference, it's about the rate law. There's what is known as the rate law for SN1 reaction and the rate law for SN2 reaction. So about the SN1 reaction, we simply define rate as rate is equal to the constant multiplied by the substrate. Okay, this is for SN1. But when you're talking about SN2 reaction, we simply define rate as the rate is equal to the constant, then multiplied by the substrate, then multiplied by the nucleophile. So what does this suggest? This suggests that in SN1 reaction, or when you're considering the first order nucleophilic substitution, the nucleophile, or the concentration of the nucleophile rather, does not affect the rate of reaction. So in SN1, we are saying the rate is just the constant multiplied by the concentration of the substrate, while in SN2 it is the constant multiplied by concentration of the substrate multiplied by the concentration of the nucleophile. So the concentration of the nucleophile just affects the SN2 reaction. It does not affect the SN1 reaction. Then the other difference which we must be able to spot out, it's about molecularity. As I mentioned earlier about the molecularity of SN1 reaction, we said that it is unimolecular. What I simply mean by unimolecular, it means that in SN1 reaction, it is just a slow step, one molecule, which involves one molecule rather. It is a step which is slow and it involves one molecule. When I say it is unimolecular, but when you're talking about or referring to SN2 reaction, which is the nucleophilic substitution second order, we say for this type of reaction it is bimolecular. And what I simply mean by the word bimolecular, it means that it is quite it is quite a single step reaction, but it involves two molecules. No wonder we are saying it is bimolecular. Then apart from that, let's understand the substrate preferences. The substrate preferences for SN1 and substrate preferences for SN2 reaction. So the substrate preferences for SN1, we start with tertiary. So for SN1, it favors more tertiary, then secondary, then primary. Then if at all you have a methyl, then it will go down to methyl. So for SN1, we start with tertiary. Tertiary is more favored than the secondary, which is more favored than the primary, which is more favored than a methyl. Okay, that is about the substrate preferences. So it prefers more substances which are in tertiary than secondary, and it does not prefer more substances which are in primary state. But when you're talking about the SN2 reaction, for SN2 it favors more substances which are methyl, so substrates which contain methyl, then it goes to primary primary carbons, then it goes to secondary carbons, then to tertiary carbons. So we must be able to understand that. Then one thing I should mention here is that for SN1, a substance which is in secondary carbocation, it is mostly favored than these other substances. But for SN2 reaction, a substance which is in tertiary, in this case, it is least favored as compared to a substance which is in this other state. Okay, so you should take note of that. Then when you're talking about a nucleophile, the condition or the state of a nucleophile, when you're talking about SN1 reaction and we're referring to how the nucleophile is, this one favors more a weak or it could be a strong nucleophile. So for SN1 reaction, it can be a weak nucleophile or a strong nucleophile. Okay, so that is what we must understand there. But when you're talking about SN2 reaction, this requires just strong nucleophiles. So SN2, this one requires just the strong nucleophile. So for SN1, a weak nucleophile is a strong nucleophile can be used, but for SN2, it prefers more nucleophiles which are very strong. Okay, so that is what we need to understand there. And when you're talking about the solvent which are used in this nucleophilic substitution. For SN1, it prefers more polar protic solvents. This one prefers polar protic solvent. And what I simply mean by polar protic solvents, these are solvents which contain a hydrogen. That's where the name protic comes from. So solvents of kinds like water, other than water, it could be solvents like an alcohol. So it could be methanol, it could be ethanol, and these other kinds of alcohols. But when you're talking about the SN2 reaction, it prefers more a solvent which is polar aprotic. Okay, this prefers more solvents which are polar aprotic. And what I mean by polar aprotic solvents, these are solvents such as acetone, or a solvent which is DMSO. So we'll look at this and we'll understand them better. Then, when you're talking about the stereochemistry of nucleophilic substitution second order and also nucleophilic substitution of first order, so the table continues here: SN1, SN2. So when you're talking about the nucleophilic substitutions in relation to stereochemistry, one thing we should understand here is that for SN1, there's what is known as the racemization. When you're talking about racemization, this is just a mixture of retention and inversion. So in SN1, there is what is known as racemization. Okay. So in SN1, there is what is called racemization. So for SN1 reaction, there is what is known as racemization, and we said racemization is just a mixture of retention and inversion. While when you're talking about SN2 reaction, for SN2 reaction, there is no racemization. But in this type of reaction, there's what is known as a complete inversion configuration. So here there is complete inversion of configuration. So what I simply mean when I say complete inversion of configuration is that, for example, if a substance was R, the first compound which was given had R configuration, meaning that once it undergoes what is known as SN2 reaction, there will be the inversion of configuration, so it will turn into S configuration. So from R, it will go to S. So that is what it simply means. Then the other thing you must take note here is about the rearrangement. Okay? About rearrangement here, in SN1, it is very possible for you to form that rearrangement because there is the formation of carbocation. So rearrangement is possible because there is what is known as a carbocation rearrangement. Okay? Arrangement. So for this one, there is carbocation, which is carbocation reaction where there is a rearrangement. Okay, so there is a carbocation rearrangement in SN1, but in SN2 there is no carbocation rearrangement. So in this type of reaction, it is not possible. Okay, or there is no carbocation rearrangement. Then when you're talking about the energy profile of SN1 and SN2 reaction, for SN1 reaction, there is what is known as two energy maxima transition states. Okay, this one has what is called a two energy maxima. There's a two energy maxima transition state. Okay, but when you're talking about this SN1 reaction, for this one, I mean SN2 reaction, there's just one energy maximum transition state. So that is what we need to understand here. For SN1, there is two energy maxima transition state, but with SN2, there is one energy maxima transition state. So about the mechanism, to summarize everything I've talked about. So when you have SN1 reaction, for this SN1 reaction, one thing you need to understand is that there's a living group. Okay, so a living group is able to live. So we are saying living group lives. Okay, once that living group lives, there is the formation of carbocation. A carbocation is formed. Then, if at all they asked you about the rate determining step, this is the rate determining step. Once the carbocation leaves, it is slow and it is rate determining step. Then the next thing which happens in this type of reaction is that a nucleophile now is able to attack. So a nucleophile attack, okay, it attacks now the carbocation. So that is what we need to understand there. But for SN2 reaction, this is a fast reaction. And why I'm calling it to be a fast reaction, it is because a nucleophile attacks from the back while the living group lives simultaneously in one concerted step. So it is just one step reaction. So this type of reaction, we are saying a nucleophile attacks. A nucleophile is able to attack. Once that nucleophile attacks, then there is the nucleophile attacks from the back. Then the living group is able to live. So living group lives once that nucleophile attacks from the back. So the living group is able now to live. So that is one thing we must understand about these two reactions. And I can give you an easy memory trick. For SN1 reaction, it is one molecule in rate low. It is one molecule. So there is a carbocation intermediate formed, and it involves two steps. But for SN2, it is two molecules in rate low. Now we are saying that for SN2, it is rate is equal to the constant multiplied by the concentration of the substrate multiplied by the concentration of the nucleophile. In that case, we said that the nucleophile is able to take part, or the concentration of the nucleophile is able to bring about the fluctuation of the rate, maybe the increase or the decrease of the rate, because of that nucleophile being present. Okay, that is what we need to understand from there. And an example of a nucleophilic substitution in first order reaction, an example I can give is this one. So I'll say example here for SN1 reaction. For SN1 reaction, for example, let me say we have a tate butyl bromide. Tate butyl bromide. A tate butyl bromide, tate butyl is simply a structure of that kind. So tate butyl bromide, when it reacts with since we are saying that it favors more chloric solvent, when it reacts with something like water, it will form the product which is tate butyl. So tate butyl bromide plus the water, it is able to form tate butyl alcohol. And this is an SN1 reaction. But when you're talking about a second order nucleophilic substitution, this is whereby you have, let's say, a methyl. And in the first case, we're able to react a tate butyl because we said that for SN1, it favors more the compound which are in tertiary state. Okay, so it favors more compound which are in tertiary state than secondary. No wonder we were able to use that bulk molecule which is tate butyl bromide. But when you're talking about this SN2 reaction does not favor substances which are in bulky state. For example, something like tate butyl. So it favors more substances which are in primary state or in primary carbocation, then secondary, then tertiary, just like that. So in this case, we can use something like a methyl bromide. A methyl bromide is a substance which is just something like this. That is a methyl bromide. Then when you react it with something like an hydroxide, then you're able to form a methanol plus the bromide. So this is what we need to understand about SN2 and SN1. Now let's get to solve these exam questions which we have. So the first question, it was okay, this is the first question. So the first question is saying that 2-bromo-2-methyl-propane reacts with water to form 2-methyl-2-propanol. States the type of reaction which is occurring. So this is the first question which we have here. Okay, so this is our first question. So let's get to solve this question. So 2-bromo-2-methyl-propane, okay, react with water to form that compound. All right, so I'll use the screen which is here. So 2-bromo-2-methyl-propane. So propane is this structure. Then they are saying 2-bromo. So 2-bromo, it is 1, 2. At carbon number 2, we should have a bromine, and also we should have at this same carbon we should have a methyl. Now we are saying 2-bromo-2-methyl-propane. So this is 2-bromo-2-methyl-propane. Then it is reacting with water to form that alcohol. So it is reacting with water. So we have water in this reaction. Okay, so it is reacting with water. So we can see that this substance is quite a bulky group. Okay, because it is a bulk group and they're asking us to state the type of reaction occurring. So we are going to say this is a nucleophilic substitution of first order, because for SN1 reaction we said SN1 reaction is able to favor the tertiary, and we can see that this carbon is a tertiary carbon. Okay, this is a tertiary carbon because it is a carbon bonded to 3 other carbons, so it is tertiary. So the type of reaction is simply an SN1 reaction. So we've solved the first question. Then that is part A. Then they are saying in part 2, draw the complete SN1 reaction mechanism. Draw the complete SN1 reaction mechanism. So this is what we are doing here. Alright, so this is the reaction taking place. So the first thing, I'm going to draw this same structure like that. So we have a bromine like that. Then the first thing we mentioned here is that the leaving group first is going to, right, so we said the first thing is that the leaving group is going to leave, which is the bromine. Once it leaves, there is the formation of a carbocation. So what we are going to have is that carbocation. So we formed a carbocation here, carbocation. Then of course with the bromide which has actually left. Then the second thing, as we said, for SN1 it is a 2-step reaction. So this is our step 1. Then the second step, this carbocation now which we have formed is being now attacked by a nucleophile. In this case, the nucleophile which we have, it is simply water. So there is water which is coming to attack this carbocation. So since this oxygen has lone pairs of electrons, it is coming to attack this carbocation. Then what is now being formed will be this. It will be now this this water attached there. Okay, this is the water which has been attached. It has attacked this carbocation and we have this structure. Now you see, one thing we need to understand here is that this oxygen now has 3 bonds. Because this oxygen has 3 bonds, it will be positively charged. Okay, so there will be a positive charge on this oxygen. Then the next thing is that that bromine which left, because it had some lone pairs of electrons, it has left, so it is coming to grab now this hydrogen there. Then the bond will be broken, then taking back the electrons to this oxygen, hence neutralizing the charge. Then what is going to be formed as a major product now will be this alcohol. So the alcohol now which is going to be formed, so this will be the product. So the product, which is an alcohol, will be this structure now. Then with OH remaining there, because this bromine has grabbed this hydrogen, then the bond is breaking to bring back the electrons to this oxygen, because oxygen is more electrophilic. So we are going to form that alcohol plus a hydrogen bromide. Okay, this other product. So these are the products we are going to form. Okay, now let's look at the second reaction. The second question they asked, which is question C. So in this question they are saying identify the rate limiting step, and we said that for the rate limiting, as we are saying in the introduction, we said the rate limiting is the first step where the the bond between carbon and the bromide bond breaks to form the carbocation. That is the rate limiting step. So we are saying that rate limiting step, the rate limiting step is just the step where this reaction is occurring. So the rate limiting is this step where the bond between the carbon and the bromine is breaking. Okay? Carbon to bromine, when this bond breaks, that is the rate limiting step. Then the second step, they are saying explain why a tertiary alkyl halide undergoes an SN1 reaction more readily than the primary alkyl halide. So the answer here, which we must be able to give, it is because the tertiary carbocation are more stable. Okay? The 3 alkyl stabilization there. For tertiary carbocation, we said that they are in this state, right? This is the tertiary what? This is the tertiary alkyl halide. Okay, so it is able to undergo an SN1 reaction more readily than a primary alkyl halide. And the answer we must give there, it is because the tertiary carbocation are much more stable, because the 3 alkyl groups will be able to stabilize the positive charge through what is known as the inductive effect, or maybe by hyperconjugation. So primary carbocation are not that much stable. So primary carbocation or carbocation are very unstable. So the reason here for part D, the reason we are able to give it is because the 3, it is because the 3 alkyl groups are able to stabilize the positive charge. Okay, they're able to stabilize the positive charge, and this happens by what is known as inductive effect, and also what is known as hyperconjugation. Okay, so that is what we need to understand there. Now let's move on to the next question. So the next question is 1-bromopropane reacts with an aqueous sodium hydroxide to produce propan 1O. State the type of the reaction occurring. So let's solve this question. So they are saying 1-bromopropane. So propane, it is actually 1, 2, 3. So it is 1-bromopropane. 1-bromopropane. So this bromine is at carbon number 1, like that. So we have 1-bromopropane like that. It is reacting with aqueous sodium hydroxide. So aqueous sodium hydroxide like that. Okay. Then they are saying state the type of reaction occurring. So we can see that all the carbons here, are just primary carbons. They are primary alkyl halides. Because they are primary alkyl halides, one thing we must be able to understand here is that for primary alkyl halides, they are mostly favored by what are known as SN2 reactions. Okay, they are favored by SN2 reactions. So the type of reaction occurring here, it is simply an SN2 reaction. So that is one thing we must be able to understand there. So what is going to take the reaction which is going to take place here is that when you have this reaction, this is what happens. So the one bromopropane like that. Then we have a nucleophile which is a hydroxyl group. So this nucleophile, because the oxygen has lone pairs of electrons, is going to attack this carbon there, which is bonded to oxygen. Then at the same time, this bromine is going to leave. Okay, so this happens at the same time. The nucleophile attacks. Once it attacks this carbon, the bromine is able to leave. So this is what we are going to form. So we'll have this group. Okay, let me just write it say this. So we'll have this group like that. So in this case, we are simply forming what is known as the propanol. Okay, so we are forming propanol. Then the bromine which left will be that structure there. Okay, so with the bromine which left, so that is one thing we should be able to understand there. So the hydroxyl attacks, and as we can see, the hydroxyl was able to attack from the back. Then the bromine left, but this was occurring at the same time, so it was occurring simultaneously. Then the next question is okay, so draw the complete SN2 reaction mechanism showing the backside attack of the hydroxyl ion. So we've drawn this. Then the third question is explain why the reaction occurs in a single step. So the answer to this question, it is because the bond formation between the nucleophile and the carbon occurs at the same time. So as we are saying that the bond is breaking between the carbon and the bromine, which is a living group, there's no carbocation intermediate which is formed. Okay, so for that reason, it is able to occur in a single step. So that is the answer we must give there. So see, we are going to say bond breaking. The bond breaking between carbon and the bromine is occurring simultaneously. Is occurring simultaneously as the nucleophile attack. That is what we need to state there. Then the next question is state the stoichiochemical outcome of an SN2 reaction. So for SN2 reaction, there is just a complete inversion of a configuration, which is also known as a Wardan inversion, and it occurs at the chiral carbon. So this one occurs just whereby you have a carbon bonded to 4 different groups. If it is a chiral compound, something like that, something of this kind, let's say we have this compound like this. So we have a bromine there, then we might have a halogen, something like this. Then we have, let's say, OH. Or OH like that. Then bonded to maybe something like this. So if it is a chirocarbon, something like that, which we have, then this nucleophile leaves. So this leaving group leaves. The nucleophile is going to attack backside, and there will be an inversion which is going to take place. So if the leaving group was on a wedge, meaning that the product of this reaction will have the nucleophile forming at a dash. So the nucleophile will be now on a dash. For example, if it is so let me write it like this. Okay. So if you have this, okay, so let me write it in this manner. The hydrogen is the one which is there. Then we have this. So meaning that once it undergoes inversion, what is going to be formed will be that the nucleophile will now be attacked at this dash. Sorry, so it should be on a dash. The nucleophile will be on a dash. Then we'll have the hydrogen now on a wedge. Then we'll have this group like that. So this is what is known as this is what is called inversion. So this is what is known as inversion. Okay, so that is what we need to understand there. Now let's conclude by looking at the graphs of SN1 and SN2 reaction. So if you've been asked to draw for SN1, as I said, there is carbocation formation. So the graph moves like this manner. So it moves like that. Okay. To move like that. Okay. So this is for SN1. Then for SN2, okay, so for SN1 reaction, it's moved like that. Then we have this group, okay, plus the nucleophile attacking this side. So if this is the graph, we have like that. Then here there is energy. Then here this is for SN1. So this is the reaction occurring. This compound plus a nucleophile. Then we'll have a rate limiting stage, which is here, where the carbocation is, the leaving group is able to leave. That is the rate limiting stage. Okay, that is the rate limiting stage, which is more like a transition stage. Then we'll have a carbocation, then plus a nucleophile which has left there. the leaving group which has left, then plus a nucleophile. Okay, plus a nucleophile. So that is an intermediate. Okay, that is an intermediate. Then the product which we have will be this now product. Okay, so this is the graph for SN1 reaction. So it's moved like that, then it's moved like that. So that is one thing we must know about this graph. Then when you're talking about the graph for SN2 reaction, for SN2 reaction it is just in this manner. So on this x-axis we have SN2, then on the y-axis we have energy, of course. So for SN it moves like this. Okay, so it moves like that. So to move like that man. Okay, then we'll have this group, this compound react with the nucleophile on this side. Then this is the product we are forming, plus a nucleophile plus that group which left. Then here for SN2 we'll have what is known as a transition state. So we'll have a state whereby the nucleophile, before the nucleophile departs, okay, there is a state where the nucleophile before it departs, and also the nucleophile before it attaches and before the leaving group departures. So we'll have this state. This state is what is known as and it has a maximum energy, so we do not hit with the 2 positive charge. This is what is known as a transition state. So there is a transition state. So you can show even in the reaction, like for example, if you had something like an arrow, then with this group, then plus a certain nucleophile, and this is for SN2, the one I'm talking about. So there will be a situation whereby this will leave, then there will be a backside attack to this compound. Then this is occurring at the same time. There will be a situation whereby before this leaving group leaves, we'll denote it with this. So we should have shown this. I should have mentioned this when doing the SN2 reaction. So there is this transition state. So before the X, which is the leaving group before it leaves, and also before this this nucleophile attaches. So before this nucleophile attaches, you show it with a dotted line. Then you put it in these brackets. Then you can put the plus like that to show that it is actually a transition state, and this state has a lot of energy. Yeah, and it is very unstable. This stage, it is very unstable and it has high energy. Okay, that is what we need to understand. So we've come to the conclusion. Thank you for watching. For subscription, you can inbox the number which is here on WhatsApp or a direct call. Then you can also email if you want to subscribe to the Meticulous Study Hub app and also the website. You can email using the email address shown there. Thank you for watching.